Hi, this is Dr. Bricker here with some hints for homework number 9, which covers mostly Chapter 8 and Chapter 14, with one problem from Chapter 9 on angular momentum and one problem from Chapter 10 on rotational kinetic energy. Okay, let's get started. So first one is an angular momentum problem from Chapter 9, so go back to Chapter 9 and read the angular momentum section. And in this problem, ice skaters often end their performances with spin turns where they spin very fast about their center of mass with their arms folded in and legs together. Upon ending, their arms extend outward, proclaiming their finish. Not quite as noticeably, one leg goes out as well. So suppose that the moment of inertia of a skater with arms out and one leg extended is 2.9 kilogram meters squared, and for their arms and legs it's 0.9 kilogram meters squared. If she starts out spinning at 5.8 revolutions per second, what is her angular speed when her arms and one leg open outward? Okay, so try to visualize it. Figure skater is spinning. When they bring their arms in, they actually spin faster. When they have their arms out, they spin slower. Okay, let's take a look at this. Okay, so we have a moment of inertia of 0.9. This is with arms in, spinning at 5.8. We want to know when the arms and one leg goes out, making the rotational inertia greater, what is the angular velocity then? So this is the case where you're spinning fast, and now you're going to spin slower because the moment of inertia has gotten greater. So the initial angular momentum, so L is angular momentum, is equal to the final. Actually, this is final the way that the problem is worded, and this is initial. So angular momentum is I times omega. Same thing over here, I times omega. Note that the omega that we have is not in SI units, but the answer we want is not in SI units, so we'll just be careful and see that the units come out correctly. And we're trying to figure out this omega 1, which I think they're actually calling the final because we're starting here and ending here. Okay, so a little bit of algebra. I2 omega 2 over I1. And then if you notice, this is kilogram meter squared, this is kilogram meter squared. Those units cancel out. And if you have omega in revolutions per second, we end up in revolutions per second. Okay, so it's a nice linear relationship we have here. Next we have one from Chapter 10, going back and looking at rotational kinetic energy. An energy storage system based on a flywheel, which is a rotating disk, can store a maximum of 3.3 megajoules, so 3.3 times 10 to the 6th joules, when it's spinning at 15,000 revolutions per minute. And we want to know what is the moment of inertia of the flywheel. So this wheel is rotating. You had to put some energy in it to get it to rotate, and you can store energy there. I mean, friction eventually will dissipate the energy, but if you have a big flywheel turning, it's storing energy for you, and you could utilize it later for other purposes. Let's take a look at this. Okay, so the energy we have here is rotational kinetic energy, and we have 15,000 revolutions per minute. We want to know the rotational inertia. So rotational kinetic energy, this is from Chapter 10, is equal to 1/2 I omega squared. Just to refresh your memory, regular kinetic energy we had before was 1/2 mv squared. We don't need this formula for this question, but I just wanted to show you the parallels between these formulas. Each of them have a 1/2. Now instead of m, we have I, so it's a little more complicated. I is related to the mass, but how's the mass distributed? And then this is the rotational velocity, whereas this is the linear velocity. So this is what we can use for this problem. Good, so the rotational kinetic energy times 2 divided by omega squared will give us I here. It's a little bit of algebra. And we were given the rotational kinetic energy. This is not quite omega yet. this is a frequency in revolutions per minute, we've got to turn it into radians per second for it to be in SI units. So if you have 15,000 revolutions per minute, we know that 1 minute is 60 seconds, so the minutes cancel out. And 1 revolution is 2 pi radians, and then the revolutions cancel out. So then you actually have omega in SI units. Okay, great. So now you have omega, rotational kinetic energy is given. You can figure out the rotational inertia. Okay, so here's the first one from Chapter 8. Chapter 8 is called Equilibrium and Elasticity. The equilibrium part is balancing forces, like we did in Chapters 4 and 5, but also balancing torques. So for something to be in equilibrium, forces and torques must be balanced. Okay, so for this problem, a 58 kilogram student stands on a very light, rigid board that rests on a bathroom scale at each end. Okay, great. We want to know what is the reading on the left scale, what is the reading on the right scale. And they tell us it's a very light, rigid board, so we could assume that the board itself doesn't have any mass. All right, let's sketch this. Okay, so here's my picture. Here's the left scale, here's the right scale, there's the person standing on it, and I've included the forces on the rod. So normal left, that's really the scale reading of the left scale. Normal right, that's the normal force on the board from the right scale. I put mg here. Really, this is the normal force from the person on to this board. So the mg here is equal to the normal force from the person on the board. I just wrote it as mg to maybe make it a little clearer. Now, if we're just going to do this problem with forces, right, the forces have to be balanced. Whatever forces are up, normal left plus normal right, those are both upward. They have to be equal to the force on the board from the person, which is equal to mg. Perfectly good. The only problem is I've got 2 unknowns in one equation and I can't solve that. So I can't just do this problem with forces. I can do it with torques though. So again, I don't know normal left, I don't know normal right. Let me pick this as the pivot point. And then the forces about that pivot point have to be balanced. The nice thing about picking this as the pivot point is normal right at the pivot point doesn't produce a torque. Right, it's right at the pivot point. So let me write this and then we can talk about it. Normal left times the distance to the pivot point, that would make it rotate clockwise, has to be equal to the torque from mg. So this would be the force, and then the distance to the pivot point, and this distance here is 0.5 meters. So I'm balancing torque. So this is really torque from normal left is equal to torque from mg. So this is looking at torques. Torque from normal left, making it go this direction about the pivot point, is equal to torque from mg, which is this force, and then the distance to the force. And then I put in the details. Normal left times 2 meters, right? Force times the distance to the pivot point, the perpendicular distance to the pivot point, is equal to mg, and then this is the perpendicular distance to the pivot point. Remember, torque, perpendicular distance times the force from the previous chapter. And then I can figure out what normal left is. mg times 0.5 meters divided by 2 meters. Okay, so that you can get normal left that way, and then you can go back to just the force equation and figure out what normal right is. Or if you wanted to, you could pick this as the pivot point and do the same thing that we did to get normal left. So either way. Okay, 8.5. You're carrying a 3.6 meter long, 25 kilogram pole to the construction site when you decide to stop for a rest. You place one end of the pole on a fence post and hold the other end of the pole 35 centimeters from the tip. And then we want to know how much force you must exert to keep the pole motionless in a horizontal position. So we definitely need a nice sketch for this problem. Okay, so here's what I have. Here's the pole. It's 3.6 meters long, and this pole actually has mass The previous question, it was a light rod, so it didn't have any mass, but this pole here actually has mass. 3.6 meters long. Here's the end that's resting on a fence post. Here's the part that's resting on the person's shoulder, and it's 0.35 meters from the end. And we want to figure out how much this force is. So mg, it's a uniform shape, so that's right in the center. We want to figure out what this force is. The normal force from the shoulder onto this pole that we have here. Okay, so just to be complete, there's also a normal force here. Maybe I can call this one normal from fence or something. And this is just normal from shoulder, so I'll put a little s there for shoulder. Okay, so if we were looking at forces, we could try to do this with just forces. Upward forces, normal shoulder plus normal fence is equal to mg. Perfectly good. The only problem is we don't know normal fence, so we can't find normal shoulder. And that's what we're trying to figure out, the normal force from the shoulder. So we can't just do it with forces. We could try torques. So let me pick this as the pivot point. And you can pick any point that you want to. I'm choosing this as the pivot point because if this is the pivot point, this doesn't cause any torque about that pivot point. So the torque from the shoulder would make it go clockwise. It's got to be equal to the torque from the actual weight of the shape here, making it go counterclockwise. And same thing, torque is perpendicular distance times the force. So this would be normal shoulder, and then the distance to the pivot point here. So looks like 3.25 meters. That would be 3.6 minus 0.35. So 3.25. And that's going to be equal to the mg, that's a force, and then the distance to the pivot point, 1.8 meters. And then the only thing that you don't know is normal shoulder, and you can do a little bit of algebra to come up with that. The key to doing these equilibrium problems is to have an accurate picture. It's a really important point here, because not only is it forces, where are the forces acting? And a picture really clears that up. Okay, next one is 812. If you hold your arm outstretched with palm up, the force to keep your arm from falling comes from the deltoid muscle. Assume that the arm has a mass of 4 kilograms. Okay, good. And angles shown in the picture. Okay, so 15 degrees. Here's the center of mass of the deltoid. We want to know what force must the deltoid muscle provide to keep the arm in this position, and then by what factor does this force exceed the actual weight of the arm. Okay, so as I said, it's key to have a good picture, so let's take a look at that. Okay, so here's the arm. Here's the actual center of gravity of the arm, so this is where mg is acting. So if you hold your arm out, center of gravity, this is the force on the arm pulling it down. Here, this is the deltoid muscle acting at some angle. So that's a lot greater distance from the pivot point to the center of gravity, twice as far basically as the distance to the actual deltoid muscle here. Okay, so you have to do a force much greater than just mg to keep your arm level there. So again, a picture's essential. Let's try balancing the torques about this pivot point. The little wrinkle with this problem is this force we could break into components. This is the perpendicular part of the force. This is the parallel part of the force, so F parallel. What we want when we're talking about torques is to figure out the perpendicular part of the force. So perpendicular part of the force times the distance. So again, we're balancing torques. The torque by F, by the deltoid muscle, has to be equal to the torque by mg. This torque making it rotate counterclockwise, this torque making it rotate clockwise. If it's not going anywhere, those have to be balanced. So the torque by the deltoid muscle, perpendicular part of the force, times the distance, and they give you the distance here, 0.17 meters, has to be equal to the torque by mg. So the force is mg, and then the distance to the pivot point is given as 0.38 meters. Okay, so you can figure out the perpendicular part of the force right now. Just do a little bit of algebra. The question actually wants how much is the overall force. So this is back to being theta over here. So if you have the perpendicular part of the force from the torque, you have to do a little bit of trig to figure out this this component here, the overall part. So basically, it looks like the sine of theta from this picture is the opposite side over the hypotenuse, and then you can get the force that way. That picture might not be that clear. Let me redraw it over here. F perpendicular. This is F parallel, and this was theta. That's where this is coming from. Okay, good. Okay, a uniform beam, length 1 meter, mass 30 kilograms, is attached to the wall by a cable as shown. The beam is free to rotate at the point where it attaches to the wall. We want to know what is the tension in this cable. Again, essential is a picture. And that's what I have here. Here's the beam. It's a uniform beam, so the center of gravity is right in the middle, 30 degrees. What's holding this beam up? Well, it would want to rotate this way. The tension's holding it up. And then there's some additional forces here at the wall. There's probably some kind of normal force this way, maybe some kind of friction that way, you know, keeping this thing from falling. We just want to know what the tension is, though. So if I pick this as the pivot point, I don't need to know how much this normal force is or how much this frictional force is. I know there has to be a normal force this way because this tension has a y part and this tension has an x part if I break it into components. So whatever force is to the left, Tx, has to be balanced by some force to the right. Whatever forces we have up, Ty and F, have to be equal to mg down. So if I just tried to do this with forces, it would be difficult. Tx is equal to the normal force, but I don't know either of those. That's just looking at horizontal forces. Vertically, friction plus Ty is equal to mg. So I can't get Ty this way because I don't know the frictional forces. So just trying to do this problem with forces at this point is impossible. I still have torques, though. So I can pick this as the pivot point. Again, picking this as the pivot point, then I don't need to know what F and N are because they don't provide a torque about this pivot point. They don't make it rotate about this pivot point. So the torque by mg, making it rotate this way, would have to be equal to the torque by T, making it rotate the other direction. So force, that's the perpendicular part of the force, it's the whole thing in this case, times 0.5 meters has to be equal to Ty, that's the force, that's the perpendicular part of the force, right, this is perpendicular, times the distance to the pivot point, 1 meter. Okay, so really similar to the last problem. From this you can figure out Ty. They actually want T, so you'll have to do a little bit of trig to figure out the overall tension. So if you know Ty and an angle, you can get T. Okay, so another part of Chapter 8 is elasticity, and we're stretching things essentially, sort of like a spring. And in this problem, we have what hanging mass will stretch a 2.7 meter long, 0.65 millimeter diameter steel wire by 1.3 millimeters. And the Young's modulus of steel is 20 times 10 to the 10th newtons per square meter. Okay, let's take a look at this. Okay, so here's my wire. It's 2.7 meters long. The diameter of the wire is 0.65 millimeters, so milli means times 10 to the minus third. Just be careful with the units. We're stretching this by 1.3 millimeters, so again times 10 to the minus third in meters. Young's modulus is given in the problem for steel, 20 times 10 to the 10th newtons per square meter. Good. So in a way, it's a nice problem, because if you're stretching something, this is the only formula that you have for stretching something. So the force that you put on a wire is going to be equal to Young's modulus times the area. This is the cross-sectional area. So area pi r squared pi d squared over 4. It's the area of a circle. L is the actual length, and then delta L is how much we stretch it by. And in this problem, we're stretching it by attaching a mass to it. So the force here is actually equal to mg. So if you attach a mass here, it's going to stretch the wire. The force that you're putting on the wire then would be equal to mg. It's not always the case, but in this problem, that's how we're stretching it, by attaching a mass. Okay, so then we have mg, putting that in here for the force, Young's modulus, area, length, times delta L. So you have everything to figure out m, right? That's what we're actually trying to figure out, the mass that will stretch it a certain amount. So you have everything here. Just be careful, Young's modulus is given. You'll have to calculate the cross-sectional area, but you can do that because you're given a diameter. Delta L is how much it's stretched by. Again, be careful with the units. And then L is the original length. Okay, good. Okay, so we're stretching a wire in the previous one. This one we're compressing a bone. It's the same idea. So and you can review page 236 to 239 for this problem. The normal force on the ground, on the foot, can reach 3 times the runner's body weight when the foot strikes the pavement. Okay, so picture that you're running, your foot hits the pavement. The normal force on your body is 3 times your actual weight when you do that. By what amount does a 52 meter long femur, okay, so that's the original length, 52 centimeters, so 0.52 meters, of an 83 kilogram runner compress at this moment? So there's a force on the femur because the person's running, and how much does it actually compress during this impact? Let's take a look at it. Okay, so really similar to the stretching of the string, the femur length 52 centimeters, so 0.52 meters. The mass of the person 83 kilograms. Luckily in this one they just give you the cross-sectional area. You don't have to calculate it. Young's modulus for a femur also given. So we want to know how much this femur is actually going to compress, and we're told that the force on the femur is 3 times the person's weight. So when you hit the ground, there's a normal force on your foot. They're telling us it's 3 times the weight. So that's the force that's going to compress this femur. So back to the same equation we had before. Force, Young's modulus, area divided by length, times the amount that it's actually compressed. And that's what we're trying to figure out in this problem. So I can put in this for the force, 3 mg, Young's modulus, area, length, delta L. And then the only thing that you don't know is how much it's compressed. Just be careful with the units again, and solve for delta L. Okay, so now we shift gears and go to chapter 14, which is on oscillations, really simple harmonic motion, and we're going to focus on section 14.1 through 14.4, mass on a spring. We're not going to cover pendulum motion. In this problem, when a guitar string strikes the A note, which is 440 hertz, what is the frequency? Okay, so we're given that the frequency is 440 hertz, and we want to know the period. Well, frequency is 1 over the period. So period's 1 over the frequency. So if you know the frequency, you automatically can know the period by this simple relationship. Remember what a hertz is. A hertz is a 1 over a second. So in this problem, when we have the period, it's equal to 1 over the frequency. So 1 over 440, 1 over seconds. So you'll see that the answer actually comes out in seconds. That's the amount of time for one oscillation. Okay, simple harmonic motion is motion that continually repeats itself. There's a restoring force trying to get us back to the equilibrium position. And let's take a look at it in this problem. An air track glider attached to a spring oscillates between the 11 centimeter mark and the 60 centimeter mark. Okay, good. The glider completes 14 oscillations in 37 seconds. We want to know what's the period. So again, the period is the time for just one oscillation. So we want to know the period. What is the frequency? Okay, great. If we know the period, the frequency is 1 over the period. And then what is the amplitude of oscillation? And finally, part D, what is the maximum speed? Okay, let's take a look at this. Okay, so we're oscillating between the 11 centimeter mark, 60 centimeter mark. So it's a mass on a spring. It's going here, passing through equilibrium, and then going back here, and it continues. This is called the amplitude here. Okay, so but anyway, for the first part, we want to know the period. That's the time for one oscillation. So it takes 37 seconds for 14 oscillations. This will give us the amount of times for just one oscillation. So that's what the period is, the time for just one. So 37 divided by 14. The frequency is 1 over the period. Okay, so once you have the period, you can get the frequency. That's part B. Part C is the amplitude. We need to figure out this distance here. Well, we can get the total distance between 11 and 60. So we'll get this total distance. That's really 2A. 2A is equal to 60 centimeters minus 11 centimeters. So twice the amplitude. That looks to be 49 centimeters. So then the amplitude would be half that. Okay, I'm not sure if they want it in meters or centimeters. Just be careful when you enter that. Okay, so 24.5 centimeters. And then the maximum speed, so make sure you read through the beginning of chapter 14. The maximum speed is the amplitude times 2 pi frequency. And that'll give you the maximum speed. So once you get the amplitude from part C, you have the frequency from part B, put it all together to get the maximum speed. So the maximum speed actually occurs here when it's passing through equilibrium. This is actually where it stops. You don't need to know that for this problem. I'm just taking it a step farther. Excellent. Okay, the next one, you can model the motion of a bumblebee's wing as simple harmonic motion. Okay, excellent. So once you know that, all the simple harmonic motion equations come into play. A bee beats its wings 250 times per second. Okay, so that's really the frequency, isn't it? It's how many things happen per second. So oscillations, vibrations, beats in this case. So the frequency is 250 hertz, and the wingtip moves with a maximum speed of 2.5 meters per second. Okay, so you know the maximum speed and you know the frequency, and what we want to figure out here is what is the amplitude. Okay, so it's really similar to part D from the last problem. So you can get the amplitude from the maximum speed formula. Just be careful, we want it in millimeters here. Okay. And the last one on the homework, we have a 507 gram mass oscillating with an amplitude of 13 centimeters on a spring, and we're given the spring constant. We want to determine the period and determine the maximum speed. Okay, let's take a look at this. Okay, they tell us we have simple harmonic motion, so again, immediately we have all the formulas for simple harmonic motion. A very useful one is the period is the square root of 2 pi m over k. So this is the mass on the spring. This is the spring constant. And in this problem, they actually give us the mass. They give us the spring constant. We can figure out the period from this relationship. The power of this is, if we know it's simple harmonic motion, this was derived for you in the chapter. This is the period. It's really complicated if you think about it. The mass starts out, say, here's the mass, where x is equal to 0. You stretch it out to here, and you let it go. This is the amplitude. It's going to accelerate to the left. This is where the speed's going to be the maximum. It slows down, stops, goes back and forth. The speed keeps changing. The force keeps changing. It would be really hard to figure out the period if you didn't have this relationship. You couldn't just take this distance and divide it by the time. That would give you the average speed, but it would be a lot more complicated because the acceleration keeps changing. So this is the way to get the period. And part B, the maximum speed. Same idea. The maximum speed we've already seen. It's the amplitude times 2 pi f. You have the period, you can get the frequency, or if you want to write it like this, amplitude 2 pi over the period. That works as well. Okay, excellent. If you have any questions, email me, and I'll talk to you soon. Bye-bye.